Bismillahirrahmanirrahim, dear students. Today we are going to learn about the earth pressure theories in the part first of this lecture. This is our week 9th of the midterm, lecture 9, 5th semester, 3rd year, BSc Civil Engineering Technology. You can access this lecture at portal.soot.edu.pk. So let's begin our today's lecture. Okay, so classical theories. Classical lateral earth pressure theory. The solution of the lateral earth pressure problem was among the first application of the scientific method to the design structures. Two of the pioneers in this effort were the Frenchman Charles Austin Coulomb and his Stockman W.J.M. Rankine. Although many others have since made significant contribution to our knowledge of the earth. Basically, more than 50 theories have been still present regarding the lateral earth pressure, but among them, the two theories are most significant and can give you a realistic result. The one is the Coulomb theory, and the second one is the Rankine theory. So, theory in 1773. And published in 3 years later, Coulomb 1776, while Rankine present his theory in 1857. Rankine present both the active and passive earth pressure theories for the passive and the active earth pressure, but just only for the soil having C is equal to 0. For the cohesionless soil, Rankine only present has theories for the active and passive earth pressure just for the cohesionless soil. But the Coulomb present has theory for the C soil and for the cohesionless soil. But he present his theory only for the active earth pressure. But we are going to learn about both of these theories. Rankine theory and his assumption. The soil is homogeneous and isotropic, which means C, pi and gamma have the same values everywhere, and they have the same values in our direction at every point. This discussion will be expanded later to consider layered soil, which each layer has different value of C, pi and gamma. The most critical shear surface is a plane. In reality, it is slightly concave up, but this is a reasonable assumption, especially for the active cases, and it simplifies the analysis. The ground surface is a plane, although it does not necessarily need to be level. The wall is infinitely long so that the problem may be analyzed in only 2 dimensions. Geotechnical engineer refer to this as a plane strain condition. The wall moves sufficiently to develop the active and passive condition. The resultant of the normal and shear forces that act on the back of the wall is inclined at an angle parallel to the ground surface. So, with these assumptions, we can treat the wedge of the soil behind the wall as a free body and evaluate the problem using the principle of statistics, as shown in figure 1a. Now, if you want to find the active condition, you have some kind of the formulas. If you want to calculate the active pressure, you have this formula, and if you want to share at the active condition, then you have this kind of formula. If you want to calculate the coefficient of active earth pressure, then you may use this type of equation. But if the magnitude of the K is usually between 0.2 and 9. If your answer is between the 0.2 and 0.9, then your calculation is correct. The equation is valid only when beta less than or equal to theta. If beta is equal to 0, it reduces to. If the beta is greater than 0, then use this equation. But if the value of the beta is equal to 0, then you may use tangent square 45 degree minus pi divided by 2. And if you have therefore the theoretical pressure and shear stress acting against the wall and the alpine and the stresses, normal stresses and detention stresses, then you may use this type of equation. And here it is the what is mean by the alpha, normal stresses, unit length, active air pressure, inclination of the ground, and the wall height. However, observation and measurement from a real retaining structure indicate that the true pressure distribution as shown in figure 2 is not triangular. This depends because of the wall deflection, arching, and other factors. Okay, now here we have this kind of the figure. This is basically the weight of the weight per unit length. This is the shear basically. This is the PA divided by B, and this is the tension. This is the normal stress, and this is the beta. Same in this diagram. This is the distribution. This is the theoretical distribution, and this is the actual distribution. Now we are going to conduct an example. We have a 6-meter tall cantilever wall retain a soil that has the following properties. Soil properties is the cohesionless soil, angle of internal friction is equal to 30 degree, and unit weight is 19.2 kilonewton per meter cube. The ground surface behind the wall is inclined at a slope of 3 horizontal to 1 vertical, and the wall have moved sufficiently to develop the active condition. You may have to calculate the active earth pressure. Determine the normal and shear forces acting on the back of the wall using Rankine theory. So first you have to calculate the beta. You have to solve a trigonometric equation of tangent inverse 1 divided by 3, which will give you 18 degree. Now the k is equal to, this is the equation for the k, because beta is greater than 0. Now we are going to use this equation. So the answer is 0.415 in the range of 0.2 to 0.9. So our calculation is correct. Moving on, now we are going to calculate the active earth pressure. Here is, we have the equation. Putting the values in calculating, we have an answer of 136 kilonewton per meter. Now we want to calculate the shear. So we have this kind of equation. Putting the values and calculating, 44 kilonewton per meter as the answer. These results are shown in the figure 3. This is basically 1.3 kilonewton per meter cube. H into at a distance of h divided by 3. And this is the shear along the surface of the wall, 42 kilonewton per meter cube. This is the beta, and this is the wall height. Passive condition. Rankine analyzed the passive condition in a fashion similar to the active condition, except that the shear force acting along the base of the wedge now acts in the opposite direction. And the free body diagram becomes shown in the figure 1b. Notice that the failure wedge is much flatter than it was in the active case, and the critical angle is now 45 minus pi divided by 2 degree from the horizontal. The normal and shear force is P divided by B and Vp divided by V respectively. Now we have this kind of equation for the passive earth pressure. For the shear we have this kind of equation, and for the coefficient of passive earth pressure this. Equation is valid when only beta is less than, beta is equal to 0, it reduces to this. Kp tangent square 45 degree plus pi divided by 2. The theoretical pressure of shear, and for the normal stresses and shear stresses we have this kind of equation. Now we have example 2 on a passive condition. A 6-story building with plane dimension of 150 feet multiplied by 150 feet has a 12 feet deep basement. This building is subjected to horizontal wind load, and the structural engineer wishes to transfer these load into the ground through the basement walls. The maximum horizontal force acting on the basement wall is limited by the passive pressure in the soil. Using Rankine theory, compute the maximum forces between one of the basement wall and the adjacent soil, assuming full passive condition develop, and then convert it to allow forces using a factor of safety of 3. The soil is a silty sand with C mean A. This is the cohesionless soil. Theta is equal to 30 degree, and unit weight is 119 pound per foot cube, and the ground surface surrounding the building is essentially level, mean the beta is equal to 0. Kp tangent square 45 plus pi divided by 2, just because that there is no beta, the ground surface is level, so it becomes the 3. Okay, PP divided by this, and we give you formula this. This is, there is no need of such kind of, we have a PP divided by B into gamma square Kp cos beta divided by 2. Here we have this kind of answer. A reliable passive forces is equal to this. The 3860 divided by factor of safety of 3 to 1290 kilo is the answer. The actual design computation for this problem will be more complex because they must consider the active pressure acting on the opposite wall, sliding friction along the basement floor, and many other factors. So this is basically a theoretical calculation, and the real and realistic calculation you have to consider the active pressure, the friction on the wall side, but we are just going to conduct a theoretical calculation. So this is it for today's. Hope you will learn something. In next class, inshallah, we will learn about the classical lateral earth pressure theories, Coulomb theory. So thank you so much. If you have any query regarding this lecture, let me know in your portal@su.edu.pk. Allah Hafiz.